In this video, we are going to do an example where we find the outward flux of a vector field across the circle of radius 3 centered at the origin. So I want to begin by giving you a chance to try this problem. So pause the video for about 5 minutes to try this on your own. So pause it in 3, 2, 1, pause and try this. Okay, so hopefully you did that. Let's talk about it now. All right, so I want to begin by drawing the path. So let's go ahead and draw our axes. So I got my y-axis, got my x-axis, and then it talks about the circle of radius 3 centered at the origin. So I can draw that in. So I'll draw in my circle. So it's hitting 3 on the x-axis here and then 3 on the y-axis. And it talks about the fact that this is the outward flux. So that means when I draw my normal vectors, my vectors that are perpendicular to the curve at a point, I want those normal vectors to be pointing outwards. So the unit normal vector, rather than inwards like this. Okay, and well, based on that, we've seen that as we're traveling along the curve, that the normal vector should point to the right, which happens if we're traveling this way, if I'm traveling counterclockwise. If I was traveling clockwise, then what would appear to be to the right would be this way, which is inward. So because the problem tells me it's the outward flux, that is enough to tell, okay, I have to be going this counterclockwise direction along the circle. All right, so from there, let's remember that the formula for flux across a curve is you take the line integral over the curve, which I'll call C, and then you do your vector field dotted with that unit normal vector, ds. And now I'll talk about a bit of notation. When I have a closed curve, which means it starts and ends at the same point, I can indicate that by drawing an O in the middle of my integral. And that just makes it clear to whoever's reading it that, this is clearly a closed curve, line integral. I don't have to put that in, but it's just a nice stylistic thing to do. Okay, so to do a line integral, I have to parameterize the curve. So I need to parameterize the curve. And we've done it for circles plenty of times. X is r cosine t, so that's 3 cosine t. Y is r sine t, so that's 3 sine t. And then to go around my circle, we let t go from 0 to 2 pi. And I could check that if I plug in t equals 0 into this. Well, cosine of 0 is 1. Sine of 0 is 0. So x and y become 3 and 0. So that'll get me to this point. And if you let t be 2 pi, you'll get to that same point. And then in between, as t gets bigger from 0 to 2 pi, we go around this circle. Okay, so I got this parameterization. Next up, I need to find this normal vector. Remember that to find the normal vector, we start off by drawing this tangent vector. So in the direction of the curve, the tangent vector, what I call the unit tangent vector, t hat, would point this way. And the formula for t hat is you take the velocity vector, you divide it by the length of the velocity vector. And we've seen before that the velocity vector, well, we take the derivative of each of these. So I write that as a vector. Derivative x is negative 3 sine t. The derivative y is 3 cosine t. And this will get divided by the length of the velocity vector, which I'll leave it as it is because something quite nice is going to happen to it later. Okay, and now let's use this to find the normal vector. So my normal vector, the normal vector also needs to be a unit vector. So I need to preserve the length. So let me keep dividing it by this same constant I have on the bottom. Sorry, what I mean to say is the same scalar that I have on the bottom. So on the bottom, let's keep dividing by the length of the velocity. And on the top, I'm also going to preserve these components that I have, but just switch the order and switch the sign. So I'll move 3 cosine t to the front. I'll move 3 sine t afterwards. And I'm going to make that 3 sine t, I'm going to switch the sign of it to make it positive there. And I could check now that if I take the dot product of these two vectors, on the denominators, I just have these scalars, so they will just multiply each other. And then when I dot these two vectors that I actually have, when you multiply the x components, you'll get negative 9 sine times cosine. multiplying the y's, you get positive 9 sine times cosine. So those will add up to 0. So I see that when I do this, the tangent vector dotted with that unit normal vector, it's 0. So they are perpendicular. They are normal to each other. Okay, the one thing I have to be careful about is, wait, that's not the only way I can get a perpendicular vector. I could have also gotten it, instead of switching the sign of this component, I could have switched it on the cosine component. So I could have done negative 3 cosine t first, and then keep the sign one negative, negative 3 sine t. Keep dividing by that length of the velocity vector. And conceptually, what these two things indicate is one of them is this outward pointing normal, one of them is this inward pointing normal. And how can I tell which one's which? Well, in our previous videos, we've used some logic to help us determine that. Like, often it was clear either from the portion of the path that we were looking at that, maybe the normal vector always has like a positive y component, if that was the part of the path I was limited to. But on this full circle, depending on where I draw my normal vector, x could be positive, x could be negative, y could also be positive, and y could also be negative. So I don't know if that's really going to help us. So let's instead look at a specific test value for t. So maybe I'll take the t value 0, and I know that at that time we are at this point. And at that point, if I draw my normal vector, it would be pointing outwards. So that would be to the right, my normal vector. So let's just figure out when I plug t equals 0 into both of these formulas for the normal vector, which one gives me a normal vector that's pointing to the right like this. So if I do plug in t equals 0 into this first one, well, I notice that the x component will be negative 3, the y component will be 0. So if x is negative and y is 0, that would be pointing to the left. So that can't be it. That can't be it. Whereas if I instead plug it into this one, the x component is 3, the y component is 0, and that would be pointing to the right. We might notice that, wait, wouldn't that not be doesn't that have the wrong length? I need this normal vector to have length 1. And that's why dividing by the length of the velocity will come in. That will normalize it and make it a unit vector. Okay, so this is the normal vector that we want. So now we're ready to start evaluating this line integral. We convert this to a regular integral, where t goes from 0 to 2 pi, 0 to 2 pi. And for our vector field, we have to plug in our parameterization into our vector field. So for x, we're going to let it be 3 cosine t. And for y, we're going to let it be 3 sine t. So that'll give me a vector where for x, we're plugging in 3 cosine t. And then for this y, we're plugging in 3 sine t. So 3 sine t. And then that whole thing should get dotted with my normal vector, which is 3 cosine t, comma, 3 sine t. That whole thing divided by the length of the velocity. And we still need this ds. We still need that ds, which we've seen for line integrals. That just becomes the length of the velocity dt. And this is nice because the lengths of the velocities here, they cancel. Okay, so now I'm ready to do the dot product. So I got this integral from 0 to 2 pi. And doing the dot product, if I multiply these x's together, I'll get 9 cosine squared t, and then multiplying the y components together, I'll get 9 sine squared t. 9 sine squared t dt. Well, 9 cosine squared plus 9 sine squared, that is equal to 9. And the integral of 9 is 9t. I can plug in the 2 pi and the 0 and subtract. So I'll get 9 times 2 pi, which is 18 pi. And that's my answer. That is my flux here. We just got it. So the last comment that I want to make about this is we will eventually, actually pretty soon, learn a drastically simpler way to evaluating this flux when I have a flux like this across a closed curve. So stay tuned to that. We'll learn a big theorem that'll help us calculate this more quickly. So in terms of our goals for this section, we finished the second goal, which is how do we calculate the flux of a vector field? We've learned how to do it across one-dimensional curves. And before that, we talked about how to do it across two-dimensional surfaces.